This is the second Chandrasekhar lecture and the first of the technical lectures by Professor Rob Myers, and he'll be talking about holographic entanglement entropy.
Okay, thank you. So I have to start the talk by apologizing because I'm sure that no one will be satisfied with the material that I present. It's probably at a very low level, but I know there are some non-experts in the room, so hopefully they'll appreciate some of it. For the experts, I can invite you to ask insightful questions and entertain yourself by seeing me squirm when I don't know the answers. But we'll see how it goes. So holographic entanglement entropy, like any title where you have holographic something or other, it's a mashup. What the string theorists are doing are stealing some good idea from another area of physics. So in this case, entanglement entropy, which is something, well, I talked about yesterday, but it's something that's used in condensed matter physics, quantum information, but it's also appeared in the context of understanding black hole entropy. And the holographic comes because we want to put it in the context of the ADS-CFT. And so the idea, the basic idea, this first arose in work that Shinsei Ryu and Tadashi Takeyanagi, they wrote a paper in 2006, so about 8 years ago now. And again, I'll say, just because it's fun, that just earlier this fall, they won the New Horizons Prize for developing these ideas. But the basic messages here are that this idea, holographic entanglement entropy, is part of a dialogue that's been developing between string theorists or holographers, people working in the ADS-CFT correspondence, and theorists in a variety of other fields. So in this case, it might be any one of condensed matter physics, quantum information. And so it's an interesting interplay of ideas. There's a new perspective that helps us learn both about entanglement entropy in the context of those areas, but we can also take the perspective of these areas and hopefully gain new insights into holography or the nature of quantum gravity. Okay, so I've got a lot of slides. There's a lot of material. I don't think we're going to cover all of it, but this is an overview so that we know where we're going. I'll talk a little bit about entanglement entropy in the context of quantum field theory. Then for a very brief lightning introduction again to the ADS-CFT. Then we'll look at the basic ideas of the holographic entanglement entropy. And then we'll do some more advanced topics, some ideas that I presented both with Aninda and with Cassini and Huerta in recent years. And then if we get there, there's one slide of conclusions. But let's get started. Entanglement entropy in the context of quantum field theory. So this is my slide from yesterday where I introduced quantum entanglement. And so this is really the thing that makes the quantum world different than the classical world. But what we would like is some diagnostic that tells us when some systems are entangled and to give us a measure of that entanglement. And the diagnostic that is going to be the hero of the day in this lecture is entanglement entropy, where what we're doing is we're taking our favorite quantum system, we're just dividing it into two parts, and then we're using entropy as a measure of the correlations between those two parts. So the recipe here, we take our system, divide it into two, A and B. We integrate out or trace over the degrees of freedom in B. That leaves us with a density matrix describing what's left over in subsystem A. Then we just apply von Neumann's formula. Trace rho log rho, throw in a minus sign, and that's what we call the entanglement entropy. Now, in simple systems of spins, like some state like this where I've got two spins, it's a simple exercise to carry out a calculation like that. So for example, if we start here and we trace out that second spin, we end up with a density matrix that looks like this. So we've got two eigenvalues, alpha squared, beta squared. And so we plug it into this formula and we get this as the entanglement entropy. Now, on the other hand, if I look at this state and I do the same exercise of tracing out the second spin, I get a more complicated density matrix that looks like that. And the only point of putting that on the screen is to say that log rho here doesn't mean I build a matrix which as components has the logarithm of the components of each component of rho A. Rather, I think of this formula as being a sum over eigenvalues, log eigenvalues. And so what we have to do is we have to find the eigenvalues of that density matrix, which turns out are 0 and 1. And then if we plug those in here, we find that the entanglement entropy for that particular state is 0. But that's relatively easy to see. What I did in going from the previous state to this one is I flipped that spin. And so now I have a product state. And so these spins over here just don't care, or they aren't correlated with the second spin over there. Hence, we're getting 0 for our entanglement entropy. So another exercise for physicists is let's think not about spins, but think about our other favorite system in quantum mechanics, probably the first one that we looked at, namely the harmonic oscillator. And to talk about entanglement, I'm going to introduce two harmonic oscillators, but I'm going to connect them with a term like this. So basically what I have are two masses here, each with a spring of, well, the masses are 1, so the spring constant is just omega squared on both sides. And then there's a connecting spring here with a separate spring constant, omega squared. Now, if I want to solve this as a quantum mechanical problem, the first thing I do, or even as a classical problem, the first thing I do is I find the normal modes. Namely, I re-express this in terms of x plus and x minus. So there are two, in this case, two simple normal modes, the one where the springs move together, and this spring in the middle isn't activated, or the other normal mode, the two masses are moving out of phase. And so that gives us, well, those two modes are described by x plus and x minus with the corresponding frequencies w plus, and this should have been a w plus minus squared. So now I have in this framework, I have two independent simple harmonic oscillators. And so I can do something like write out the ground state wave function for this system here. And so I just have my ground state wave function for this oscillator and for this oscillator, and I multiply them together, and I get something like that. But now I'm going to go back to my original coordinates, x1 and x2, and this ground state wave function now takes this form here. So I might want to ask, are the x1 and the x2 entangled? So I'd trace over one of the degrees of freedom, and so I chose here to trace out oscillator 1 or to trace over x1. And so I take my ground state wave function and its conjugate, and the tracing over just means that I identify the x1 entry in both of those and integrate over x1. Those are just Gaussian integrals, and so I end up with another Gaussian here with some complicated coefficients that are built out of the omegas and the frequencies that I gave up here. A simplifying limit that helps us understand what's going on is the case where this frequency is much, much smaller than the basic frequency little omega squared. And in that limit, this first coefficient is just basically omega. And so this is basically just the product of psi naught dagger for a harmonic oscillator with frequency omega. And then there's this beta term here with the product of these two, and that is proportional, well, it's some ratio, but it's proportional to this other frequency, capital omega, the one for the connecting spring. And so if I look at this density matrix, I can see that it's not a product of some function of x2 times some function of x2 prime because of this term here. And so this is really telling me that the system is entangled. But that makes sense because where is the entanglement coming from? It's coming from this connection between the two oscillators, which translated down the page into this beta coefficient. As that capital omega goes to 0, this beta is going to go away, and so I'm just going to be left with a pure state density matrix here. But I said that how I wanted to measure the entanglement was with entanglement entropy, and so I had this formula. Again, log rho, or to evaluate this, I want to identify the eigenvalues of this density matrix. And so there's some eigenvalue problem that has to be solved here. And luckily, Mark Cernicki, who I'm stealing all of this from, has done that problem for us. And we find the eigenvalues given in terms of this C, which is in turn given by these constants, which are built out of the omegas at the beginning of the problem. But when I go through and I evaluate this, summing over all of these eigenvalues, you get an entanglement entropy that's given by an expression like that. Again, a simplifying limit to think about is the one where capital omega is becoming small. And in that limit, this C variable is again proportional. Well, it's proportional to the ratio of those two omegas. And it's becoming very, very small. And you can see that the entanglement entropy is also proportional to some power of omega. And there's also this logarithm of omega sitting there. But it goes also, the entanglement entropy goes to 0 in this limit that capital omega, or this spring constant for the spring connecting the two oscillators goes to 0, as we might have expected. So that's another simple example of applying the idea of an entanglement entropy to some physical system. Oh, sorry, was there a question?
Very familiar with some differences. So it's a nice concrete example, just in case anyone remembers those, you might want to relate them.
The one comment I wanted to make, or one comment here that I wanted to make, is I'm getting entanglement in the system because I'm insisting on working in this original basis, this x1 and this x2, and tracing out one of those variables. And there I'm guided by, well, what I called the physical narrative. I'm guided by the picture that I was given, or I gave you, on the first transparency. If I thought about the problem in terms of x plus and x minus, I wouldn't have found any entanglement. That was a description where the two oscillators, or these two modes, were decoupled. Similarly, if I hadn't given you the picture, but I had just given you that potential, you might have thought, well, this is some two-dimensional oscillator, and it just happens that the potential isn't circularly symmetric or rotationally symmetric in the x1, x2 plane. Rather, it's easier to vibrate. So these are supposed, this x1, x2, and these are supposed to be lines, equipotential lines, according to this potential here. And so it's easier to vibrate along this axis than it is to vibrate along that axis. And if that was the problem that we were thinking about, these axes, or x1 and x2, are just some coordinates, and they wouldn't have really taken any precedence. And so we might have thought about integrating out any axis, any variable in that problem, and we would have found that sometimes there's entanglement. Well, typically there is entanglement, but if we integrated out very special axes or very special variables, coordinates, that the entanglement goes to 0. But again, in making this choice, I was being guided by a particular physical intuition, or what I called the physical narrative of the problem that I was studying. So the problem that we would like to study is quantum field theory. And so here, how do we make progress? I mean, this is again a slide from yesterday. Here, what I said is an interesting problem to study is one in position space where I take a time slice. My division is a division between one region A of that time slice and an exterior region B. And I'm supposed to integrate out degrees of freedom, find a density matrix, and apply that. But how does one really think about that? Well, one can gain intuition about that by attending Raphael's lectures last year, apparently, or by just souping up the problem of simple harmonic oscillators that I studied before. So I can think of a free scalar field as just being many, many coupled oscillators. And so here I've drawn, again, a picture that gives me the physical narrative, or it tells me the system that I want to study. And so I've got a lattice of different masses. There are various springs by which each mass is oscillating on its own, and then there are various springs coupling the different masses. And so what do we have here? The red springs, there's a spring constant that I've called mu squared. It's convenient in a moment to call the spring constant connecting them 1 over delta squared. And I've reinstated a mass for each one of the particles, which I've called delta to the d power d minus 1. Because although I've drawn a two-dimensional lattice, I'm thinking, well, I'm actually thinking of it as a lattice in d minus 1 dimensions. And then with time, that means I'm in a d-dimensional theory. So again, the physical narrative is one where I have a lattice of oscillators. But that delta is really the lattice spacing, or in a moment, we'll be talking about the short distance cutoff.
What are those red springs?
Those are going to turn into the mass in a moment. So if I take the continuum limit, you know, the phi's turn into a phi of some position. These p's over the appropriate power there turn into the momentum density. This sum turns into the integral. But that mass indicated that I had a massive scale, or that spring indicated I was talking about a massive scalar field. And so there's a mu squared term as well as a gradient term appearing in my Hamiltonian. So again, the intuition is to think in terms of these oscillators and the lattice. But given a field theory like this, the first thing that we do is we do a Fourier transform. And the reason we're doing that is we're finding the normal modes of this particular system. And so in terms of the K modes, or the momentum modes, I have a bunch of decoupled oscillators. And that's really then the starting point of our grad school or our textbook field theory courses. And much of what we do now is we add interactions up here and we perturb these free harmonic oscillators in various interesting ways, and well, we do lots of other stuff. But again, for this particular context, I'm guided by this picture, and I want to do a calculation in the position basis, or in position space, when I'm calculating the entanglement entropy. So one of the things, given this set of oscillators here, we could do is we could calculate a ground state wave functional in parallel with what we did before. And so each one of these modes has a Gaussian wave function, and if we take the product of all of them, we end up getting a sum in the exponential, and so we're given a ground state wave functional that roughly looks like that. But that's just a whole product of the simple harmonic oscillator wave functions. This, again, is in the normal mode basis. I wanted to work in the x basis, and so in that basis, we would start with some expression. Well, actually, all I did is I took the expression I had before and translated it back to the x basis. And you find Now that there's some more complicated expression, it's still Gaussian if you like. There are two phis up here, but there's some complicated or more complicated kernel connecting the x or the phis at different values of x. At this point, one in principle could apply this or go back to the oscillators and calculate an entanglement entropy in your favorite configuration. I'm not going to do that, but I'm just going to describe some of the results that one runs into. And so the first comment that I made yesterday was that, in fact, without a regulator, the calculation would diverge. By presenting the theory as a theory on a lattice, we naturally have a regulator, namely the lattice spacing. So there's a short distance cutoff. In that context, if I do the calculation, then the result is given by powers of that short distance cutoff over some macroscopic scale that characterizes the size of my region up here. And there are various powers of that, and those powers depend on the dimension of our space-time. Well, it's really this, well, I'll just say this line. So if I do that calculation, not just for one shape here, but I choose many, many different shapes, what I find is that the numerators here all have a geometric interpretation. And so in particular, a result due to Raphael is that this first term is actually an area law. The numerator here is just the area of that surface. So we live in 4 space-time dimensions, and so I see an r squared, and so that really is an area over delta squared. Well, here it has the dimensions of area, but if I interpret it, if I do it for many different surfaces, I'll always find the same coefficient, the area, and then the cutoff to the appropriate power. I'm allowing the dimension of the space-time to be an arbitrary variable, but that's my idiosyncrasy as a string theorist, that I'm happy to think about space-times of more than 4 dimensions or less than 4 dimensions. But the thing is that these terms also, these divergent terms here, are also arising because of the plenitude of short-range correlations in the vicinity of the entangling surface. And so they also have a geometric structure. And so this second term would be, again, an integral over that surface, but there'd be a curvature or some combination of curvatures in there. And that's what then reduces the power here by 2, because this has dimensions 1 over length squared. And so that naturally then, well, as I increase the number of curvatures as I go up, I naturally go down in a power of 2 every time. But there was a question there.
Does that surface have to be of codimension 1?
It's codimension 1 in the spatial directions, yeah. Or it's codimension 2 in my space-time, yeah. But that's just because of the recipe was that I wanted to divide my system into 2 pieces. And so I need a surface that gives me, well, here an inside and an outside. It doesn't have to be simply connected. I could have another blob over here or many blobs, but I want to be able to distinguish 2 pieces, and well, what I've just started calling the inside and the outside of that region. So that's why it's codimension 2 in the space-time or codimension 1 in the Cauchy or the time.
Does it make sense, at least in this formulation, to ask for entanglement between a wire in 3 dimensions and whatever is outside the wire?
Well, that would be a different kind of a problem. I think what you're talking about is let's build a more complicated system where, for me, I would say that there's a cosmic string passing through the space-time. There are degrees of freedom on that string, and there are degrees of freedom in the bulk space-time. And I could ask, are those 2 sets of degrees of freedom entangled? So that's a question you could ask, but it's not the question that I'm addressing here. Here I'm asking about, all of the degrees of freedom in my field theory living in the light blue region, how are they entangled with this stuff in the green region? So that's just my question that I'm asking.
I didn't quite understand this statement about the dimensions coming down by 2, why it was. I mean, you said that the second term has this curvature terms, which are, of course, second derivatives in the metric, but
Right. It's a set. I guess I didn't say today, but so there's a divergence in the original answer, and that's arising because of short-range correlations in the vicinity of my entangling surface. And so all of these terms that are divergent are actually, you know, attached basically, or they're related to these short-distance correlations in the vicinity of the entangling surface. And so it just turns out that they have this geometric interpretation, I guess. There's. Sorry, because of the curvature, or?
Yeah, in R, for example, the first expression. In terms of R to the d minus 2, then R to the d minus 2.
This. Sorry, I'm in the wrong time zone. Oh, yeah, okay. So it's,
I think R maybe it's not clear that big R is some radius or some diameter.
oh, this was a scale. This was a size. It wasn't a Ritchie scalar. No, I'm sorry. This is a Ritchie. This is something like the Ritchie scalar. The term you might have thought appeared would be something like the extrinsic curvature integrated over the surface, and I've thrown that term away for 2 reasons. One is that I'm a string theorist and I'm really thinking about a Lorentz invariant theory, and you can argue that the extrinsic curvature actually has an index. It's a codimension 2 surface. There are 2 normal vectors, and so there are 2 extrinsic curvatures. And I really want to build a scalar to integrate it in an invariant way. And so I can't do that with a single extrinsic curvature. I could hide a k squared in here, and in fact that arises, I mean this is in bracket or in quotes because I'm not really specifying the details of what goes there, but you could have something like the Ritchie scalar, you could have something like the extrinsic curvature squared, but you don't find a term, it's not consistent with the invariance of the coordinate invariance of the theory, or the Lorentz invariance, if you just had a single extrinsic curvature. But all of that said, I've been implicitly being the string theorist and assuming that my system's Lorentz invariant. If that's not the case, if, for example, I happen to be working on a lattice, which we may get to, well, actually, that's where we started, isn't it? Then, in fact, if I'm doing this on a computer and I make bad choices of my coordinates where I'm doing the cuts, you can't actually find terms in here. But those are just an embarrassment for me. I claim that they shouldn't.
If we started off with a non-relativistic theory where the time and space are scaling differently, would you get those two?
I think you could, yes. Yeah. So in a non-relative, yeah, okay, sure. So yeah, okay, no, that's fair enough. So there was, actually that'll come up again tomorrow. There is an assumption here that I'm working with a theory with a certain amount of symmetry, but if those symmetries aren't there, then I guess this structure will change. But I do expect them all to take this local form of some integral over some geometric quantity integrated over the entangling surface. So here I'm just integrating 1. Here I'm integrating some geometric structure that's a curvature.
And also, one thing that I want to clarify that this entangling surface itself could be time dependent. I mean, it could be changing in shape, and you're just concentrating on one particular slice of that.
I mean, I could do the calculation again and again, like as well as varying the geometry here in my spatial or my constant time slice, I could let the surface vary in time as well. Okay, other questions? Oh, that's good. That'll slow me down, good. What else to say? Oh, a slight embarrassment is that these nice coefficients here or in my geometric formula are going to depend on the details of how I regulated this problem or this calculation. And so they typically don't, well, they're sensitive to the details of the regulator, and so they carry information both about the theory, the shape, and, well, the regulator. And so the regulator isn't very interesting, and so we say these coefficients aren't universal. However, if we persist and carry this expansion out to high enough orders, for example, in even dimensions, we typically run into a logarithmic divergence, then those terms or those coefficients are universal, or they do tell us information about the underlying quantum field theory. So this, wrong way, this coefficient here in this expression would be universal. And I think we may actually, we'll see an example of that, or I'll run by an example of that later in the talk. Some more general comments. Something that was emphasized after my talk is that we're working with some or I'm talking about some very non-local quantity, which is at best very difficult to measure, by which I mean is we have no accepted experimental procedure by which I can ask my friends to go to the lab and actually measure the entanglement entropy in some system. On the other hand, I'm a theorist, and so I'm not intimidated by some annoying fact like that. And one finds that this is still a very useful diagnostic, in particular in quantum information theory, where it's telling me about resources to do various tasks, and in condensed matter theory, where it might be telling me about or distinguishing different phases of matter, for instance. Yeah.
So I wanted to, this is the part I find very puzzling, and I'm also a theorist, so from one theorist to another, leaving aside the experimental side, the point of view that I take on entanglement entropy is, so it can be very difficult to measure. It can be very difficult to measure as long as there's a, at least a concept for that. So that makes it operational. So is this an operational measure here? And then let me just put it better into context, that if it isn't, then if we take James's principle of writing the state subject to the ignorance we have, if it's not possible, even in principle, to ascertain what the state is, then we would have to mix over all states. Do you get what I mean?
I think I understand enough of the question to say, let's talk about that later.
It's a good answer.
Regarding this experimental procedure. So there was this paper by Abanin and Demler which claimed to give an experimental procedure to measure the second Renier entropy.
Yeah.
So that is not acceptable.
No, but I'm talking about something else, right?
Well, if
you're talking about Renier entropies, so
but it's kind
they're different.
But in some limit, if you were able to measure all the Renier entropies, you can analytically continue, right?
In an optimistic world, perhaps. Yes. I said, oh, I should have said, yeah, I should have put a word yet. So it's an interesting research problem. Perhaps there are, there are ideas. There's the one you mentioned. There's a list of ideas. But they focus on, I think, the Renier entropies, not directly the entanglement entropy. What else have we got? Oh, yes. Where did the people on HEEntropy, or people like me, first run into entanglement entropy? Well, it really had to do in the context of black holes and the Bekenstein-Hawking entropy, which I talked about yesterday. So our black holes here, actually the event horizon carries an entropy, which is very puzzling, or seemed very puzzling. And Raphael here actually, in some sense, invented entanglement entropy when he was exploring how you might explain the origin of that entropy. So this goes actually back to a time when people didn't put the words entanglement and entropy next to each other, but he did a calculation which we now think of as a calculation of entanglement entropy. And he noted that this area law here that I talked about is very suggestive, or it's very similar to the area law you find in black hole entropy. Usually people thinking about entropies were thinking about thermal entropies where they expected a volume law or a volume growth. It's an extensive quantity. And so these were entropies of a different kind. And maybe if this cutoff here was of the order of the Planck scale, then this formula could be the same as that formula. So that's a beautiful idea. A lot of people, well, rediscovered that idea. There was a lot of work in the 1990s on trying to make that clearer, how that would work. Unfortunately, we found better things to work on HEPTH, and you'll see that this line of investigation kind of fizzled out, although there is some people who are returning to think about these ideas more actively in recent times. So I didn't really have any more to say about that, but I just wanted to make that connection to the black hole microphysics again. And then the other comment was that it's recently appeared in the context, or become very a hot topic, if you like, in the context of ADS-CFT correspondence. And so that's really the end of my intro to entanglement entropy, and so I'll pause and ask if there are any questions. We already had our questions, maybe. Okay. So the next one, I know there are a lot of experts in the room, but this will be for Barry, who maybe we can convince him to do holography calculations by the end of the week. This is my picture from last day. Again, I think of ADS-CFT as a dictionary between two different kinds of language. On the one side, we have the language of quantum field theory, or in particular, conformal field theories. There's no gravity. On this side, we have the language of quantum gravity coupled to a negative cosmological constant. So CFTs are special quantum field theories that don't have intrinsic scales. Anti-de Sitter space, or ADS, is the simplest solution of gravity coupled to a negative cosmological constant. Now, I lied to you. He's looking at his email. This is a confession to you. We don't actually know how to do quantum gravity. So when we do these calculations on this side, we're actually taking a particular limit where it's basically just classical gravity or semi-classical gravity with small curvatures. And what that means on the other side of the dictionary is we're pushing ourselves into a regime where the central charge, or the number of degrees of freedom in our field theory, is very, very large. In the case where this is a gauge theory, we think that the number or the rank of the gauge group is becoming arbitrarily large. But it's also pushing us into a regime where this theory is strongly coupled. And so that's actually a very useful regime to be in, because this is a regime where it's difficult to apply our standard techniques to do calculations here. On the other hand, classical gravity with small curvatures is a place where it's relatively easy to do calculations. And so by doing these calculations, we can gain insight into these strongly coupled field theories on this side. What else? Oh, I guess to take a little bit of a closer look at this, this is a cartoon of anti-de Sitter space. Again, it's a maximally symmetric geometry, or it's the simplest solution with negative curvature. And so here's a metric, or a line element. Oh yeah, this is the simplest solution of Einstein's equations. So there's some geometric stuff here, and what I see here is a 1 over L squared. So L squared is the radius of this curvature, and so it's a constant that comes, or it's, we're equipped with in problems when we're studying our anti-de Sitter space. There's naturally a scale in the problem, which is the scale of the curvature. And you can see in this metric that L squared appears in different places. So the story was something along the lines that the quantum field theory, in some sense, lives on the boundary in d dimensions. So that's out here. And that's our CFT. And in the bulk, we have our quantum gravity theory, or in fact, it's just our classical gravity theory that we're studying most of the time. This metric I can think of as the metric in which our CFT lives, but you can see in the bulk here, there's this extra factor, which is stretching and shrinking different distances. So if I have a certain fixed delta x, it's very, very large if I'm at large radius, but when I go to smaller and smaller r, the proper length, or the physical distance down here in the bulk, gets smaller and smaller when I keep my delta x fixed. So if I think that I have a string stretch between x equals 1 and x equals 2, the energy of that string is going to be large here, and it's going to get smaller and smaller as it drops down, or as I put it, at different places. It's also, well, it'll be important, well, it's not important, but it's good to remember that well, it's just this idea that proper distances or physical distances are shorter when we're down here in the middle of the space, and they're very, very large near the boundary. And I'll make reference to that fact in a moment in talking about holographic entanglement entropy. Oh yeah, okay, so I should have talked about the string now, but we had the string being energetic up here, but the same string stretching from x equals 1 to x equals 2 having less energy down here. And so there's this connection between energies and radii. Even though I set my h bars and c's to 1, that wouldn't have the right units, but we have this extra scale, L, and so there's a conversion between the energy and the r that's provided by that, L squared. So energy has dimensions 1 over length, so this expression now has dimensions 1 over length. And so that's all I had to say about the ADS CFT, so this is your one chance to ask a question. No questions, okay. Excellent.
What was capital N?
Capital what?
Capital N?
It was the radius of curvature of my anti-de Sitter space, so it's this parameter here that appears in the metric. Or my, my Ricci scalar, if you like, is proportional to 1 over L squared.
Why do we need anti-de Sitter space?
That's a longer story, but if you like, a simple way to tell the story is that, well, I said here it's the maximally symmetric geometry, so it has a certain symmetry. But if you go and think about conformal field theories in d dimensions, there's also a global symmetry, the conformal group, that's associated with those conformal field theories. And you can see that those two symmetries are the same. And so it's part of the dictionary that the global symmetries, or the natural symmetries of a conformal field theory, are geometrized, or they're turned into geometric symmetries of the gravity, or the space-time in the gravity theory. And so that's one of the ways I can argue that I needed an anti-de Sitter space. If I had flat space, I wouldn't have the right symmetries to describe, say, this conformal field theory. Other questions? Last chance. No, okay. So now we'll go on to a few words about holographic entanglement entropy. Again, we're doing entanglement entropy in the context of quantum field theory. In particular, we have this boundary conformal field theory. And so I'm drawing this picture, and I'm thinking that there's some conformal field theory that lives there, or in particular, a holographic conformal field theory. And we want to know what's the entanglement entropy associated with the degrees of freedom in that region A. Again, I want to take advantage of holography, or what these gentlemen showed me is how to take advantage of holography to take this difficult computation in the quantum field theory and turn it into a simpler geometric or gravitational computation. And so in the gravity, this picture also lives there, but it lives at the boundary of the ADS space. And in my cartoon, this white space down here is the bulk of the space-time. And the recipe then that these folks introduced or suggested was that I take all surfaces that hang down into the bulk, but connect up along the entangling surface in this boundary picture. On those surfaces in the bulk, I evaluate the Bekenstein-Hawking formula, or the area divided by the Newton's constant in my gravity theory. I think about all the possible surfaces with those boundary conditions, and I find the one that minimizes this particular quantity, and that minimal value is then the entanglement entropy in the boundary theory calculation. So one comment is, remember that distances were, if I had a fixed delta x, they were shrinking as I went down, and that's why the surfaces like to stretch down into the bulk, rather than, you might think in my cartoon that the smallest area would be if I just stretched across, straight across in the green region. But that's actually a very large physical distance. I can cheat, or I can go down into the bulk and find a shorter route or a smaller area because of that redshift, what I called the redshift. Another.
What does that surface end up
Why don't
being?
you asked the question in 5 slides, 10 slides, I don't know. There'll be black holes in a moment. Other comments are, I'm calling that an area, but again, I'm a string theorist. I'm in all sorts of number of dimensions. So the boundary is a d-dimensional space-time. This bulk has d+1 dimensions. This is a codimension 2 surface in the bulk, and so it has d-1 dimensions. But I still call it an area, which means that it's a codimension 2 surface. And the other one is, well, I told you, that's the Bekenstein-Hawking formula. It looks like a black hole entropy, but these surfaces have nothing to do with horizons. Another technical detail, if I'm working in a Lorentzian space-time, I should really think that I'm looking for saddle points, and so I'm looking for extrema. And rather than saying that the boundary condition is that my surface should connect on the entangling surface up there, I want to say that V, this surface, is homologous to this A, which means that I can take this surface down here and just push it up. There are no obstructions to mapping it or pushing it back up into that region A.
So is there a way to check this? Because the field theory computation that you did was weakly.
Wait. I have to explain some more things. First thing I want to explain is if you try and do that calculation, again, the answer is obvious. It's infinity. I'm trying to integrate an area all the way out here to r equals infinity. So of course, I get a big number. I get an infinite number. But that's not a bug. That's a feature of the problem, because I told you that I expect the entanglement entropy should be divergent unless I regulate it. And I haven't given you a regulator here, and so I'm getting the infinity that I should have expected. Further, what's causing that infinity is all of the area up here at large radius. But I guess I didn't tell you today, but I told you the other day that when I'm probing the geometry at large radius, I'm looking at the high energy degrees of freedom in the field theory. And so it's really because of the UV, or the high energy degrees of freedom, that I'm getting this infinity, i.e. it's the same UV divergence that I expected in my quantum field theory calculation, or that I should expect in my quantum field theory calculation. So if the problem is integrating all the way to infinity, the way to solve that is don't integrate all the way to infinity, integrate to some large radius. And that's a standard thing to do. That's equivalent to introducing a short distance cutoff in the boundary theory. And the larger r is, the smaller our cutoff is. So they're inversely proportional. Again, I need a conversion constant, but I have this L squared sitting around. And so I can write a formula like this that has the right dimensions. So if I choose a fiducial surface here at some large radius, that's thinking about the quantum field theory, or the CFT, with a cutoff, or a shortest distance scale delta, given by that formula. If I do this calculation then with this cutoff, I find that to leading order, I get an area law coming out, and that's relatively easy to see, so I'm going to show you the calculation. Here's our ADS, or our anti-de Sitter metric. This was the picture out here at infinity, so that's sort of the blue, that's a cross-section going through here. There's the entangling surface, that's the green part, that's A. What is the extremal surface doing near the boundary? Well, basically what it does is it falls straight down into the bulk. So it's not moving in this transverse direction, it's rather just going straight down. And so if I want to evaluate the area, there's some thing I'm supposed to integrate over. This little contribution, or the contribution up here, is basically an integral over the boundary directions, or these directions along the curve. And then an integral that runs straight down, or it runs in the radial direction. Each one of those factors has one of these factors. I pull out an L over R, or the square root of this term, and I stick it in there. Similarly, for each one of these directions along the boundary, those are like parallel to the x's, I take a square root of one of those and stick it down there. What is this thing with the blue underlining? Well, that's nothing but the area of that blue surface in the conformal field theory metric. It's just the area in this metric here, and all of the ADS-ness has gone into these factors, which are part of the R integral. And so I have something that's proportional to this area, and this integral, I've converted my R naught, and I've written it in terms of the short distance cutoff. I mean, there's interesting stuff down here at smaller r, but I really only wanted to see the contribution from large R, and I get an answer that looks like that. It's the area over precisely the appropriate power of our short distance cutoff, and then there's some ADS, power of the ADS scale, and a Newton's constant, which is actually, I can think of as the ratio of the ADS scale to the Planck scale to the appropriate power. And that's something that we know about in ADS-CFT in the dictionary. That combination of gravitational things is something that is related to a central charge, or it gives us a count of the degrees of freedom in the CFT. So that's, well, maybe that was a little bit too fast, but that's where we see this area law term arising in these calculations. If we persist, or if my students persist, they can also start to see this whole series appear, and if they persist enough, they can start to pick out the universal terms and the universal coefficients associated with the calculation of holographic entanglement entropy. So when this first appeared, this was just a conjecture. It was like a bunny pulled out of the magician's hat. And so the next thing that happened was that, well, most of us just ignored it, didn't see what it was good for, but a few people worked on understanding or providing consistency tests of this interesting formula. And so the first consistency test that I'll put up there, I mean, basically what they were doing is they were learning about various properties of entanglement entropy. But the first one I'll put up there was the fact that the area law naturally comes out of all of these calculations as the leading term. In 2 dimensions, one can do the calculations in conformal field theory because that's a case where there's a huge symmetry group, there's a lot more control. And so there are some nice results developed by these folks for what the entanglement entropy would be in this situation, where I've put my spatial world as being a circle with circumference c, and I've just taken an interval, a subinterval of that circle, L, and I evaluate the entanglement entropy, and what I get is an expression like this. And so there's some geometric stuff here. There's the cutoff. It's in a logarithmic. The leading term, or the leading singularity, is a logarithmic singularity. And here, what is that coefficient? That coefficient is the central charge that I talked about yesterday that appeared in various calculations, say in the Zamolodchikov-C theorem. And so there's a very pretty formula that comes out just of a conformal field theory calculation, but you can apply this in a 3-dimensional anti-de Sitter space, set up the same calculation, and you find this answer right on the nose with all of these factors appearing precisely where they should. You can do a similar calculation for a thermal ensemble, and there's also a nice formula where sines turn into cinches and temperatures appear, but I won't write out that formula. But again, you get the right answer precisely as calculated by those folks, just in conformal field theory. Another property of entanglement entropy is that if I'm looking at a pure state, then the entropy for my region and for the complement should be the same thing. That happens very naturally in this holographic context. Here again, I'm looking at my circle, so that's the boundary, and then my subinterval. If I want to ask what's the minimal surface that bounds here, the boundary of A, well, there's some surface there. But if I ask the same question for A bar, well, I've got the same boundary, and I'm going to have the same extremal surface. And so when I evaluate this, I'm going to get precisely the same entropy for that case. Where what I was talking about was just an empty anti-de Sitter space, or perhaps with a few gravitons or small excitations floating around in the middle of the space. On the other hand, there are cases where those two entropies aren't the same. So for example, in a thermal ensemble, I don't have a pure state. If I go to the ADS CFT dictionary, then there's part of an entry there is that a thermal bath is equivalent to having a black hole down here in the middle of the space. And so that creates an obstruction, or it creates a difference between the extremal surface that's homologous to A bar and the extremal surface that's homologous to A. And so what you find in that case is that those two entropies are not the same in this case, as you expected. Yeah. Well, this, yeah, then you'd want to think about, well, okay, an example of what you might think about is some kind of collapse forming a black hole. And so, I mean, it's a slight extension of their recipe, but what Hubini, Rangamani, and Takiyanagi suggested is basically I apply this formula and find extremal surfaces in my dynamical space-time. But in that case, then the horizon comes down and it ends somewhere. And so even though on, here, I'll draw a picture. So here's my ADS space. Some stuff came in and formed a black hole. Something like that. The idea is if I'm calculating an entanglement entropy here, say this is my time slice, I'm calculating some entanglement entropy. No, I'm not going to be able to get the artwork right. Let's say my surface, I mean, a possibility would be that there's a surface that runs around the black hole and joins up. And that would be, you know, that would naturally be not, well, it wouldn't, it looks like there's an obstruction here. There's this horizon that I can't push it back. But on the other hand, because of the dynamics, it's not really an extremal surface, or it's not the minimal surface that's homologous to the boundary, because I can always take this and pull it down and push it over. So it's because the black, in this case, I'm presenting it as I created the black hole, and so I can get around that obstruction. In the case I think you were thinking about, where I just had some pure state, I guess all I can say is I don't really understand what's going on in the center of the space. There's some kind of singularity, perhaps, and so I don't really know how to deal with that. But
in this case, I mean, do we have SA is equal to SA bar or not?
you would, yeah. They both, you know, both. Again, my artwork is failing. Both this region and, you know, the one that ran around, you know, this extremal surface, it's naturally homologous to this, but it's also homologous to that if I let myself pull it around and then push it out. Oh, sorry. Oh.
The surfaces here are all, they're all spatial surfaces, right?
Yes.
I mean, in the bulk.
Yes.
So in the process of doing this deformation, I mean, if you're far up enough in time,
Yes.
you know, your boundary circle is far up enough in time, then you will have to have a surface during the deformation, which is not space-like anymore. Because of the nature of ADS.
Yes, okay.
So does,
Yep.
does that matter? So, I mean, in other words, where is the time slicing? Where is that relevant in this entire discussion?
So most of what I was talking about here, strictly what they were talking about were situations where the system I was probing was static, or the geometry was static. And so that's most of this discussion. What he was pressing me for was, though, to talk about an example where there was some kind of dynamics. And so the recipe then seems to be, although it has less support, that I just apply this formula in the dynamical space-time. And so these homology arguments that I was talking about were letting me get by. But what you're pointing out is that the spatial surfaces are actually becoming time-like.
Because of the nature of ADS, it can be far away up enough.
She's saying if I go...
Horizon never reaches. You know, there's always something that goes, you know, the space like that goes beneath this, starts the horizon and comes out the other side. I don't think you need to be time like that. The horizon is a light-like surface, so I don't see why you need.
Oh, no, okay, yeah.
I'm not sure. Maybe.
Well, why don't we address that in the discussion or in the T?
One last question is, I mean, a pure state should look very close to a thermal ensemble. So
Yeah.
either we should have SA is equal to SA1 or we should have SA is not equal to SA1. You know, if you take this collapsing surface and you, as you say, maybe go late enough in time.
Yeah, okay. So my claim there was that you're seeing this equals that, but what that means is they're equal to leading order in n squared. So there may be small differences. Well, you actually want it to be equal precisely, and so that's the answer at leading order that I'm finding. So I'll go on to the next. So having this entry about black holes and thermal baths, another game we can play or we notice is that the entanglement entropy doesn't just capture in that context quantum entanglement, it also captures the thermal entropy. And so there should be a contribution to the entanglement entropy that goes like the volume of the space, and for a conformal field theory, it's the temperature to some appropriate power. So there is an extensive contribution, and that's really in the context where the size of my region is much, much bigger than the thermal wavelengths of the stuff, or 1 over the temperature. And so how does that arise in the holographic setup? Well, if I have a very, very broad region here in my black hole background, what the extremal surface does is it basically falls down to the horizon, stretches along the horizon, and then rises up again. But this part where I'm running along the horizon, I'm evaluating the Bekenstein-Hawking entropy of a portion of the horizon, but that's giving me just the right entropy density, because the horizon entropy is the thermal entropy of the thermal bath. And so I get this extensive contribution from this little part, or this part of the surface that stretches along the horizon. So version 2 of that, or the more advanced discussion there, is that if I think about the eternal black hole, so I have the Einstein-Rosen bridge, I've got 2 sides. I've been taught by Juan, I guess, to think about that as one boundary representing my original CFT, and then the other boundary on the other side, I can think of that as the thermofield double, the thing that purifies my thermal density matrix. And the the thermal entropy in that case is the entanglement entropy between these two sets of degrees of freedom. So the holographic prescription is I need a surface that's extremal, that's homologous to the entire boundary out here. But what does that turn out to be? Well, it's precisely the bifurcation surface down in the middle of the space. And if I evaluate this quantity there, I'm just evaluating the black hole entropy, and I get the appropriate thermal entropy again for the black hole. And so that's an interpretation of, or it's a connection between black hole entropy and this entanglement story that's been told. Another nice property of entanglement entropy is strong sub-additivity. I mentioned that last day. So there, what do I have? I've got two regions, A and B, and I've made them to be overlapping. And it turns out that if I evaluate the entanglement entropy for A and B separately, I get a bigger number than if I evaluate the entropy for the union and the entropy for the intersection. So how does that work in the holographic story? Well, there's two sets of surfaces here, or there's a bunch of sets of surfaces that are associated with each one of these entropies. But these two, because of the intersection of the regions, those two bulk surfaces are intersecting, or they cross at some point. And so what I can do is I can just revise the accounting. Rather than thinking of it as surface 1 or area 1 plus area 2, I think of it as this contribution to area. Well, I combine those two outer parts, and I combine these two inner parts. Now, this surface, or that, the area that's coming from that surface is in the same class as this surface over here, but I know this is the minimal area surface, and so this area is bigger than that area. Similarly, that's in the same homology class as this, but this is the minimal area surface, so that gives me a bigger number. So when I combine those two areas, that's this side of the inequality, and these two areas give me that side of the inequality. But what I argued is because of the extremization, I'm always getting a smaller answer over here than I am over there. Now, strictly speaking, again, that's in the context of a static space-time. Aaron Wall worked hard to show that something similar, or actually something technically more complicated, still works to produce this inequality in certain dynamical settings. And there are other relations that the entanglement entropy satisfies, and there's a paper by these gentlemen here that shows or argues, at least in certain contexts, that the holographic prescription satisfies those relations as well. Let's see, what else do we have? Oh, there's this connection between, or the appearance of these universal terms in the logarithmic singularity in the entanglement entropy. So I called that the universal term. And so here's a calculation that I did with two very smart people, Janet Hung and Misha Smolkin. But we've isolated the term in the holographic entanglement entropy, the universal term, in 4 dimensions. And so there we're integrating over a 2-dimensional surface, and there's all sorts of geometry that appears. And then there are various central charges that appear in those 2 slots there. And so that's a formula that was argued for by Sergei Solodukhin much earlier. But the holographic prescription, or using holography, you can precisely build up, or you can reproduce that formula on the nose. So you're getting all of this interesting geometric structure, the central charges, and the integral, and the logarithm, and the factors of 1 over 2 pi, precisely on the nose. And so that's another test of this holographic prescription. There's also then some work that we did to derive the holographic entanglement entropy for a special situation, but that was actually superseded recently by these 2 gentlemen, Aitor Lukowicz and Juan Maldacena. They came up with a proof I'm not going to go into the details of what that proof really is, but it's a generalization of the standard calculations that one would do in the context of a Euclidean path integral approach to explaining black hole entropy. And the extension is really that they're thinking about situations that are periodic, but they don't have a continuous symmetry. And really what they're doing is a careful translation of the replica trick, which I'll mention hopefully in a little while, from the boundary theory into the bulk. And what they argue is that you get both two things in Einstein gravity. First of all, the theory picks out an extremal surface, and that what it gives you is just the Bekenstein-Hawking entropy evaluated on that extremal surface. But I'm not going to say much more about it. There are experts here in the room for the people who are interested, who want more details. And I think that's the end of my introduction to holographic entanglement entropy. So at this point, I'll ask, are there any questions?
Can you just repeat what you just said? What did they prove? Not how the proof goes, but what exactly have they proven?
What they did is they thought about the replica trick in the boundary CFT, and so they talked about calculating the Rayleigh entropy and taking the limit n goes to 1, which gives you the entanglement entropy. So they translated that argument into the bulk space-time. And what they showed is that for Einstein gravity, what that translation does is it picks out an extremal surface, the Ru-Takenagi surface, and that it evaluates, or the entropy evaluates to A over 4G on that surface.
So they've proven this conjecture, at least in a under some you say static. It's underassuming static. Is that?
Yeah, I'll say yes.
Okay.
To avoid an argument.
Static and Einstein, which means what? No other fields. What do you mean by?
No, it means that I don't have higher curvature terms. You might imagine that in higher curvature theory, there's something like the Wald entropy that appears there, or something like that. How long was I supposed to go? Oh, okay. Well, we can probably make headway into this. So let's try that. So this is a, actually, yeah, okay, I'm going to start talking about the replica trick. Yeah. So, this question was posed before we knew about the proof. So the question is, why is it hard? Why is the derivation a hard thing to do? And it's really because, well, we all thought in terms of a standard approach to calculating entanglement entropy, which is the replica trick. And so there, rather than calculating this quantity directly, it's simpler often to calculate the trace of powers of the density matrix, and then to evaluate this quantity here, which is known as the nth Rayleigh entropy. But then Rayleigh put this particular factor in here because if I understand this, or if I have control of this equation for all values of n, when I take the limit, n goes to 1, that precisely reproduces the entanglement entropy. But if I think about the standard calculation, it goes something like this. Well, a standard calculation in quantum field theory. The zero step is implicitly I analytically continue to Euclidean time, and then I make a path integral representation of the ground state wave function by doing a path integral from -infinity up to my t equals 0 slice. And so I have some kind of wave functional here for field configurations on this slice. For later purposes, I'm going to divide that into an inside and an outside, and so this wave functional cares about the field configurations both on the inside and the field configuration on the outside in the B region. To build a density matrix, I want the conjugate wave function, and so that just comes from going from +infinity down to t equals 0. The density matrix came from integrating out or tracing over the degrees of freedom in the outside. And so what that means is basically there's a path integral over these, or I extend the path integral to integrating out the field configurations on my t equals 0 slice in the exterior region, in the B region. So that gives me a path integral representation then of a density matrix where I have the field configurations on the bottom of this slit and the field configurations on the top of the slit. I'm supposed to have many copies, and so I do that path integral several times. Here I do it 3 times. Then I'm supposed to take the trace of the nth power. So again, what that means is I'm sort of multiplying, but that means I'm tracing, or I'm connecting. Let's see if I can do this. So I equate the field configuration on this bottom slice here with the slice over there, and or the top of the slice there, and I integrate over all of those phi's. And similarly, I connect bottom to top, and then when I go all around, so the bottom here connects to the top of the back slice. And so you do some manipulation like that, and what that's supposed to give me is then a path integral representation of the nth power, here the cubed, of the density matrix in our favorite quantum field theory. Where implicitly I'm working with the vacuum state. Yeah, I'll just say that. And so what am I supposed to do at the end of the day to evaluate this? Well, I'm supposed to evaluate a path integral, or sometimes we might call it the Euclidean partition function, over some complicated space, which is actually an n-fold cover of the original space-time. And in fact, it has this complicated set of connections in the middle here, and so there are big curvature singularities at the edges. Another set of words, which I'm not going to get to, is I could also think of this as a path integral over n copies of the field theory on a single space-time. But what I've done is I've introduced an interesting operator at the boundaries here on the entangling surface that connects the different field theories as you move around the twist operator. But that's a set of words that I'm not going to do anything more with today. What I focus on here is this picture that I have a path integral, but it's a complicated space that in particular has big curvature singularities in it. And the problem then that we run into is that my holographic slogan is that it's all geometry. What I'm trying to do, or what we've seen many times, is I take an idea in the quantum field theory and I turn it into a geometric idea or a geometric quantity in the field theory or in the gravity theory. Oh, okay, bulk, yeah. So, yeah.
Yeah, in the previous slide you referred to evaluate. The evaluation is tractable, is it? You could do it, you can evaluate it. This part here, when you talk about it as hard, you're referring...
No, okay, what did, again, I'm talking to a computer scientist, so what did...
No, I'm just trying to figure out, when you said that that step was to evaluate, I wasn't clear on whether you could evaluate. Like you could have a formal expression.
It would be extremely difficult, but for simple theories, I can take them to my friend Roger Melko at the University of Waterloo, and he puts them on the computer and he calculates.
Okay, so you can evaluate numerically.
So in principle, I can calculate, yes.
And then you have to take a limit as n goes to infinity. So then the cost of the...
Yeah, okay, it became much more complicated, yeah.
But it often happens in this entanglement business that when we try to use the Renyi entropies, there's a beautiful formalism for it, but it doesn't work so well in a lot of cases to get the von Neumann entropy.
Yes, I agree with that. So this is yeah, okay. I don't have anything to add to that.
Okay, I don't either.
Yeah, it really only works in the simplest cases, and it just becomes really complicated. I mean, there are, even in 2 dimensions, if I go to 2 disjoint intervals, You know, there are expressions for the Rayleigh entropies for all of the n's, but we don't know how to analytically continue. They're just so complicated, we don't know what the analytic continuation should be, and so you can't.
These are for free theory, or you can add interactions?
No, those are for, actually, I think those are explicitly known for free theories, yeah, but you just can't.
But for simple cases also, so what are the simplest examples that you were referring to?
Well, okay, we're not going to get there, but the simplest example would be just 2 dimensions, a single slit. I think we saw that in your talk, didn't we, yesterday? There's a formula for the Rayleigh entropy in a 2-dimensional conformal field theory for a single interval. No, that's for any conformal field theory. It's basically the C over 3, the 1.
In high dimensions, I was talking about the numerical things that your friend Roger Meltzer could do.
That Roger can do. He can work in 2 plus 1, and he claims now he can do, he claims he can do 3 plus 1, but I haven't seen any calculation. Oh, these are, no, they're not our favorite. I mean, they're favorite condensed theory models that have some limit. I'm not exactly sure. Actually, he was working recently on various ON sigma models, so, yeah. But he doesn't calculate for all n. He calculates the second Rayleigh entropy or the third Rayleigh entropy. Yeah, no, he's not using holography. He's, yeah. So what was my story? My story was, it's hard because what I wanted to do is I wanted to turn stuff, I wanted to use ADS-CFT to translate hard QFT problems into geometry, but here we've got a singularity in the boundary, so what do we do with that when we are trying to make this geometric thing? So Forsyth was the first to think about this, and he just said, live with it. He just he claimed you should let the singularity live in the bulk of the space-time as well, and that it would be effectively extremized, or the geometry of that singularity would be extremized as part of the bulk gravity integral. Matt Hedrick complained and said, oh, that's interesting. What he said here in this empty space is that's fine, but you get the wrong answer when n is not equal to 1 at least. So for some reason that disappeared. I don't know why. But he also suggested that instead what I should think is that this boundary, this replica, or this n-fold cover sets some new boundary conditions for my bulk geometry, and I should find a smooth bulk geometry for these new boundary conditions. And in fact, he also advocated that you can use the conformal symmetry basically to smooth out the singularity, to unwrap it. And there were some examples in 2 dimensions where he explicitly carried out that calculation and evaluated the appropriate partition functions. And then I would have characterized Lukowitz and Maldacena as all of the above, in that they advocate finding smooth instanton or solutions for integer n. But then when you move away from integer n, you run into singularities, but you just deal with it. Oh, what is going on here? That's interesting. There was, okay, I over-edited this morning, I'm sorry. So here's Hedrick complaining. What did we do? Well, what we said is we'll just look for another calculation that has a simple holographic translation, but in fact, at the end of the day, we're really following this smooth it out prescription or approach that Matt advocated for. So what did we do? Well, we simplified the problem. I'm not going to do holography to start. I'm going to talk about quantum field theory, but we're going to focus our attention on CFTs because we have holography in the back of our mind. And to simplify the problem, I'm going to focus on a particular kind of entangling surface. I'm going to think about a sphere of some radius in flat space. My objective is to calculate this entanglement entropy. One of the observations is that if I evaluate a density matrix in here, that it actually describes physics off of my time slice, given that density matrix, I can describe all of the physics in what I'm calling the causal domain, or all of the points that are causally connected. That wasn't quite right. If I think of this as an initial data slice, then I can evolve forward like this. In that region, I can evolve backward, and I can tell you what all the field configurations are. So that's defining my causal domain. That takes my mind away from this time slice to a chunk of the space-time, and so there I can take advantage of the fact that I'm in a CFT, and I can think about doing a conformal mapping of that chunk of the space-time. So there's a nice conformal mapping that takes this causal domain to a new geometry where I have time, and the space-like slices are the hyperbolic plane in the appropriate dimension. The problem, well, yeah, okay. So basically what it does, the conformal mapping, is it takes this chunk or sub-piece of flat space and it blows it up to infinity, so it becomes the entire space-time. So in this new conformal frame, this is sort of a Penrose diagram of the entire space-time. It remembers about this original radius because the curvature scale here is 1 over r. Similarly, another interesting fact is that the theory here on this new space isn't in the vacuum, rather it has a temperature, and that temperature is again controlled by that same radius. So this is a CFT. I'm comparing physics in two different conformal frames, or before and after a conformal mapping. I've got in this conformal frame the theory at some finite temperature. There's an interesting thermal density matrix, but that's going to be related to the density matrix, the reduced density matrix in my original problem by some unitary mapping, but that unitary isn't going to affect the entanglement or the von Neumann formula. And so what I'll find is that the entanglement entropy in my original problem is equal to the thermal entropy in my new problem. And so what I've established is a connection between an entanglement entropy calculation that was hard and a thermal entropy calculation which is equally hard. There's some subtleties that I'm not going to talk about, but again, now we turn to ADS-CFT and we use this dictionary, or the entry in the dictionary that says thermal bath equals black hole. And so we can extend this equality one more time to say that the entanglement entropy is the thermal entropy is the horizon entropy of some appropriate black hole. What kind of black hole? Well, there we're guided by this geometry here. We need a black hole that has a hyperbolic horizon, and there is a class of black holes that satisfy the bill. In fact, it's not really a black hole. It's just a particular foliation of empty anti-de Sitter space. So this is my, well, this isn't quite the metric I gave you before, but this is a metric on anti-de Sitter space. Here's the same metric after a coordinate transformation. And you can see what's coming, well, what's coming out here is some hyperbolic slice. Here's time. GTT has this rho squared minus L squared, and so it's going to 0 somewhere. And so that's saying there's a horizon. It's really a coordinate singularity, or it's a boundary of my coordinate patch. And if I think about it, or I work a little bit, I find that there's a corresponding temperature for that horizon that's just precisely 1 over 2 pi r. The specialist should, or this may not be too much of a surprise, I talked about a story in the conformal field theory where I did a conformal transformation, but that's reflected in my bulk gravity theory. The coordinate transformation that took me between those two metrics is really just implementing that conformal transformation in the boundary theory. And this is, well, it's really, so this is a Penrose diagram of my entire ADS. With this coordinate system, I'm really just taking this little, covering this little region inside these blue slices, or those light sheets. And so this is kind of like Rindler coordinates in anti-de Sitter space. In fact, well, I've started, or people have started calling it Rindler ADS coordinates. we have a horizon, evaluate the horizon entropy. In fact, I can do that for any gravity theory using Wald's formula, and so there's some prescription, and it reduces down to a formula like this. This is the area of the horizon. This is some constant that captures all of the couplings in my gravitational theory. And so in Einstein gravity, that turns into this particular constant, where I've got the ratio of the ADS curvature scale over the Planck scale to this power, and so that was the thing that I called the central charge. More generally, if I have an even dimensional boundary theory, it turns out to be a particular central charge that appears in the trace anomaly, but for odd dimensions, I can also think of it as effectively a central charge, or it gives a count of the number of degrees of freedom in the theory. I still have to evaluate this area. That's just an integral over the hyperbolic plane. But that's going to be infinite, so I only integrate out to some maximum. And what do I do? Well, the theory, again, came equipped, well, to make sense of the calculations, what I said before is I needed to introduce some cutoff surface. And so that tells me how far to extend this integral out along the horizon or along the bifurcation surface. And so I plug that in there, and I find that the answer looks like that, or the leading contribution looks like that. But that's just precisely the expected area law. Here's some r to the appropriate power over delta to the appropriate power for my d-dimensional CFT. I can carry out the expansion of the full answer, and I can also see this central charge appearing in the various universal terms. And I think I ran out of time 10 minutes ago, so what we'll do is we'll skip to the end and say, call it a day. Oh, no, I can't skip to the end. Hi there, Spenta. So, down around slide 74. Oh no, further than, yeah, there it is. So, my conclusions. ADS CFT is an interesting playground for studying strongly coupled quantum field theories. Holographic entropy, entanglement entropy is part of this interesting dialogue between the holographers and people studying other kinds of physics. And holographic entanglement entropy is, in my mind, extremely interesting because I get to learn lessons both about properties of these strongly coupled theories, but it's also an area where in the past couple of years, or at least in the past couple of years, we're learning that it's an arena where we can learn lessons or gain new insights about the bulk theory, in particular to gain insights about quantum gravity or perhaps ideas like emergent space-time. But of course, there's my slogan, there's always lots more to explore. So with that, I'll thank you for your attention and apologize for running over.